Hey dude, let's talk about Zener regulation. This kind of mirrors your assignment. Not exactly, because I've got a motor here. It's a vibrating motor, a little tiny little vibrating motor. The purpose is a haptic motor. You can use vibrating motors for lots of things, but this is a haptic motor. A haptic motor actually goes on people, and it gives you a sense that something's going on. So it's like a physical signal. Okay, so I've got this guy, and he's got pretty high resistance, and he runs on 3 volts. And the power supply that I have here is 5 volts, coming from an Arduino. So just imagine an Arduino driving this thing. So we need to regulate it down to 3 volts because it's a 3-volt motor, and we want to regulate it at that voltage. If you make it go at a higher voltage, it'll actually vibrate at a higher frequency, but it's not designed to do that. So stick it at 3. So as far as regulation goes, this is our Zener here. This is a picture of it. That's actually what a Zener looks like. It's kind of see-through. It's pretty cool. I got this information off of DigiKey, and I'm just going with this information here. So, with that said and done, the way you solve a Zener circuit to see if the Zener is actually on, see if it's working, is essentially you look at it like this. You calculate the current going through here, and then you calculate this current. If that current is higher than this current, you're good. So the way to do that is to calculate the current through here. If the Zener is on, that means actually you're dealing with a 3-volt drop across there. So I for the motor equals the voltage drop across the motor divided by the resistance of the motor. And in that case, I put the numbers in and I got 22.06 milliamps. Okay, so now if I calculate the current going through that and it's more than 22.6 milliamps, I'm good. So let's do that. How do I calculate the current going through this? I need the voltage drop across that. And if you take a look at that, I've got my voltage source, and I know I've got 3 volts here. So the difference between that is the voltage drop across that. So the way we calculate that is we do the voltage drop across the resistor equals the voltage drop of the source minus the voltage drop across the Zener. In this case, it's 2 volts. Easy. So now I have my voltage drop across my resistor. In this case, I know the resistance. I'm going to choose a 68 ohm resistance. I could do something a little bit higher. Actually, I don't think I can get much higher than that. We'll see. We'll do the math. Okay, cool. So now to do the current here, I'm going to do the current through the resistor, which is the voltage drop across the resistor divided by the resistor. And I calculated that out to be 29.9 milliamps. Cool. So that is definitely larger than what is required for the motor, so I'm good. Now, I want you guys to calculate the Zener current. And the way you do that is you think Kirchhoff. So I know that Kirchhoff's law says at this point right here, the current going in, IT, is equal to the sum of the currents going out through here and through here. So that's going to be the Zener current plus the motor current. Solving for the Zener current, I get my IT minus IM, and in this case, it's going to be I get the number down here, 7.35 milliamps. So I do have current going through here. When you calculate this, if your Zener's off, it's not working, that is going to be a negative number. But it's a positive, so we're good. We're golden. Now, okay, you're done. I got some more to say, but if that's all you want to watch for the assignment, you're good. But I got some more stuff to talk about. Cool. So that's all you have to do for your assignment. But I just wanted to say that this resistor, I chose that resistor because what I did was I actually looked for a resistance that would allow a particular current going through here that was higher than the current I needed. And I chose a resistor that gave me just a little bit more. 29. I needed 22, and I calculated for 29. Now, if I wanted to, I could make that a 47 ohms, and at a 47 ohms, I'm going to get more current. So that's fine. I get like 40 or whatever, 40 milliamps, and that's good. And that's okay. You can just do that. But the problem with that is not really a big problem, but as you go lower and lower, what's going to happen is that you're going to have a more wattage. You're going to have more power, more energy dissipated. So you actually have to choose a resistor up here. It's not going to get hot. Plus, really, the way that a Zener regulation works is it just takes the extra power that's coming from this thing, and it just vents it into the atmosphere and makes heat. So it's kind of inefficient. So there's no need to have the amount of current that's drawn by 47 ohms. But I did do some calculations over here. If I use a 68 ohm resistor, if this guy was 68, then the power that was actually coming out of this, it's actually pretty small, is 58 milliwatts. That's at 68 ohms. Now at 47 ohms, it was 85 milliwatts. And if I actually made this a 10 ohm resistor, if R equaled 10 ohms, PR would be 0.4 watts. So you get almost half a watt, which is still not bad. So Zeners are good as long as you're not requiring a lot of current here. If this was like, I don't know, 36 ohms, it'd be a lot of current. It'd be a lot more current, and I'd probably have to go with a 10 ohm resistor, or maybe even more, or lower. So I'd have actually more current there. So yeah, that's Zeners.